Hello everyone, welcome to this tutorial. My name is Emerson Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to do trend analysis using Stenoscope algorithm in the Google Earth Engine Python API programming. So, as you can see here, when we do plotting for example, annual temperature or annual any variable, actually, it is very hard to understand how the temperature or any other variable changing from one year to another year. So it's a little bit complicated, but trend analysis allows us actually to make a single map for the whole of the time series that shows how much temperature or your desired target or variable changing through the time. For example, using the Stenoscope here, I produced a map that shows increasing and decreasing temperature, where temperature increases and where temperature decreases through the time. This tutorial, I'm going to show you how to do this procedure using Stenoscope algorithm and XEE library in the Earth Engine Python programming API. Make a new notebook in the Colab environment, and as a first step, call the necessary libraries. So let's get started with EE library and GEE map as GEE, and also XArray as XR. Now I'm calling necessary libraries to make a connection between Earth Engine and a Colab environment and Python programming language. So next we need to install a new library XEE. Import XEE. Actually, the XEE is a kind of library developed by the Google community experts that allows you actually to integrate image collection and X-ray structure that is really beneficial to apply machine learning and deep learning algorithm in the Python on Google Earth Engine data. So now install XEE first and then import it. So in the next step, we need to actually make a connection between Earth Engine and your code editor environment in the Google Earth Engine. So as you can see here, first start with authentication process from EE library already defined here. As you can see, from Earth Engine library, start with authentication and then initialize like this your account information. So according to the instruction here, first we need to initialize the Earth Engine account based on your project ID that is unique for every user, and then call the OPT URL. So the first argument here, the project equals to, now you must enter your project ID. It's very simple to find your own project ID. Just go to Earth Engine Code Editor environment, this address, upper right, in the corner, there is an icon that shows your Earth Engine account. Click on Project Info and you can find your own Cloud project ID. Just copy and paste it into the code, just like that. So, and according to the instruction, the OPT URL address also must be copy and paste here. There it is. OPT URL equals to the address here. So let's run, and a new message popped up asking for actually your Google Earth Engine account. Select and do continue and continue again. Okay, now connection is settled, and for the next step from now on, we can call image collection from Earth Engine environment first and then do the desired process in the next step. Make a new cell and let's call your desired data. In this tutorial, I'm going to use ERA5 monthly aggregates, the temperature data actually. No matter which kind of data or what is your data variable or the region of interest, you can use this tutorial for all around the world. Because in the Google Earth Engine, if you go to the browse by tags, you can find a lot of data and information. If you are totally new to Earth Engine, I suggesting you to actually watch the beginner's video in the first step, and after then start to see this tutorial, because in this tutorial I assume that you have enough information about the Google Earth Engine. You can go on my YouTube channel and find beginner videos. It is in playlist highlighted and allows you to learn about the beginner topics in the Earth Engine environment. So now, as you can see here, now I'm gonna call this image collection into Colab environment. Just copy the Earth Engine snippet just like this, but remember to make a variable first. For example, set collection to image collection around 5 monthly aggregates. Select the target band. For example, here I'm gonna work on average air temperature data available since 1979 to 2024, for example. So select the target band and filter your data based on the time span you want to work on. For example, I'm going to actually monitor the temperature variation, air temperature variation over the last 25 years, starting from 2000 to 2024, for example. As you can see, this data actually is available until 2020, but there is no problem. That actually the system only calls those of satellite data that is available. So let's run the connection and there is no problem here. In the next step, we need to identify the region of interest. In the previous tutorials, I was showing how to find the region of interest through the coordinate system and coordinate latitude and longitude. Longitude and latitude. But in this tutorial, I'm going to show you how to find your region of interest using GEE map. So make a new variable as map from GEE library. GEE means GEE map because before GEE map inserted as a GEE. So GEE dot map, make a map user interface with a base map. For example, I'm gonna have a satellite base map and then show the global satellite view. So here now you will have a user interface that allows you to find your region of interest without adding coordinate or something like that. For example, I'm gonna study on Iran, my own country, and I'm gonna showing you how the temperature varies over the last 25 years in this region. Feel free to select your own region of interest, no matter where is your region of interest. This tutorial available for all around the world. The data and platform, everything is free and you can use this for your own research study. So, but as you can see, the spatial resolution is 27 kilometer or 2000 or 27,000 meter. That shows a very coarse spatial resolution. That's why it is better to select a wide area or a big area as a study as a region of interest, because actually such kind of a spatial resolution gives you more meaningful information in the large extent analysis. For a smaller scale, you can use modest LSD data with 1 kilometer spatial resolution. So now through the geometry tools or drawing tools available here, for example, I'm gonna select draw a rectangle and easily select your region of interest. There it is. For the next step, I'm gonna have the draw region or the geometry or the rectangle as a new variable, because I'm gonna use the rectangle in the further analysis to identify the region of interest for raster layer available here. So the location equals location or ROI, up to you which kind of name you want to use. ROI equals to from map dot draw last feature. Actually, the draw last feature is a function allows you to get the rectangle or ROI from a map layer, because the map already called like this, and as the geometry is a subclass for map, now you can find the geometry using draw last feature. So to convert it as a geometry, that's geometry added. So now we have one image collection and we have a map, we have a geometry or region of interest. In the next step, I'm gonna call the data to actually multi-array structure, because I'm gonna apply time series analysis, and also I'm gonna implement the slope to see the temperature variation over this region. For example, here let me to make a new variable as dataset equals to from XR library. As you remember above here, XR actually representative, the X represents the X array. So XR or X array from XR called open dataset. Okay, what dataset? The collection dataset. And also sets engine to EE library, and CRS sets to EPSG 4326. Actually, the CRS coordinate system and EPSG 4326 shows WGS84 that is unique and same for all around the world. So not specifically used for only one region. No matter where is your region of interest, always CRS. If you want to have WGS84, the CRS will be same for all around the world. So the next is a scale, the pixel size. As you can see, the pixel size is 27,000 meter or 27 kilometer, but the scale size must be actually in degree format here. 1 degree 100 kilometer, but here 0.2 means actually 20 kilometer, or 27 kilometer will be like this. Okay, now the scale is settled. The next parameter is the region of interest. It is very important to limit your analysis to a single region of interest, because it reduces the volume of data and speed up processing in the Earth Engine and Colab environment. So another one is geometry equals to ROI. Let's run a code, but here there is a problem. I had a typo about the geometry. If you want to get more information about the X-array structure, you can search on the net about GEE or XEE library and GEE or Google Earth Engine. Then there is a good instruction on uh, GitHub that gives you a lot of information and example about the different methods about calling this data and also the different examples. So back to the topic. Let's make a print from the dataset. As you can see, this dataset is monthly and shows we have 246 months actually for the region of interest. Okay, now this is a multi-dimensional data. One dimension is time, one of them is longitude and latitude, and we have one variable that is air temperature. You can see the air temperature data information, and also here there is a short list of actually the time, the temporal period in which the data is available. our data is available from January 2000 to, for example, June 2020. Okay, for these 20 years, we have monthly temperature data for selected latitude and longitude. As you can see, it is a multi-dimensional structure. So in the next step, I'm gonna actually make a preview about the temperature variation for this region of interest. For example, I'm gonna actually convert this data from monthly to annual format. For example, make a new variable annual sets to bring the data set first and resample it based on annual frequency or YE, and then define the statistical operator for the resampling process. For example, I'm gonna get the average temperature for each year separately. So let's run a code, and as you can see, the code is running and takes a few seconds until resampling actually is done completely. If you had any problem or any question about the code and this tutorial, feel free to reach me out on my YouTube channel, and the code example is also attached below this video, and you can actually use my code to compare yours and also try to find any error and find the solutions. And otherwise, you can put your comments on my YouTube channel. I will check them out as soon as possible. So the annual data set created. Let's make a print. As you can see, 21 data is available. And also here you can see the latitude, longitude information, and data starts from, for example, 2000 to 2020. We have data for 21 years. Okay, in the next step, I'm gonna do a plotting. I'm gonna make a plot to shows how annual temperature varies from one year to another year. So let's call the annual data like this, and then select the target variable that is air temperature data. Make a plot like this and a couple of arguments necessary here. For example, x sets to longitude. As we have a dimension, we as longitude x equals to lon and y equals to or sets to lat, like this. It's very easy to do, just we need to understand about the data dimension and also about the necessary arguments in the function. I will try to share everything I know, but if you search on the net, you can find a large amount of information about NetCDF data or multi-temporal data structure. So C map or color map equals to, for example, jet, and the next one is robust sets to true. Actually, robust allows you to skip the outliers and provides better visual characteristic about temperature and ranges over the across the region of interest. So, and the next one is call. We need to define the time actually to show a multi-temporal data or multi-temporal plot structure. Call wrap sets to, for example, 7, means in each row in the multi-temporal grid, I'm gonna see a 7 image per each row because I have 21 images. So let's run it, and now you will have a grid structure or multi-temporal plot with 3 rows and 7 plots in each row separately that shows latitude, longitude, and the title, and a single plot that shows how temperature varies from one year to another year. But such kind of actually monitoring is really hard and difficult to understand if you want to talk about how temperature varies from one year to another year. And it is very confusing for the audiences or people who are reading your papers. So, the time series analysis, such as a Senna slope, allows you to make a single map to shows how temperature increasing or decreasing over the time. Let me show you. So to do the Senna slope analysis, we need to install PyManCandle library. The ManCandle is also another time series analysis or trend analysis method that I will show you how to use this in the next videos. So let's install ManCandle library. Pip install PyManCandle. This is one of the most famous algorithm in the remote sensing community for the time series analysis. So PyManCandle and then import it as mk, just like that. Now you can see the library installed and imported. Okay, now we need to actually make a function to apply the Senna slope on a data. So def is now actually helps you to make a function for Senna slope, sen function. The import argument is a image for the Senna slope function. So first of all, we need to get rid of some of the nan values. That's why here we need to we need to skip the nan values in the images. One of the advantage of X-array or multidimensional structure is that allows you to, for example, use other libraries that's not necessarily consistent with the raster layer. When you convert your data to the X-array or multidimensional structure, then you can apply such algorithms such as ManCandle or NumPy potentials on the raster data analysis. That allows you to do a lot of things that you couldn't do before. So now import NumPy as NP. For example, maybe there is not an appropriate function in the for raster layer to skip the nan values, but thanks to multidimensional structure and XEE libraries, you can see that I can use the other libraries potential to solve my issue. So clean equals to, so the input image now np.nan np.isnan. Okay, and remember to add a tilde icon here. Let's go to the search and here type for on-screen keyboard. If you don't know how to add some symbols here, I'm gonna use this symbol. For example, click on shift and tilde symbol. As you can see, it means not in the function here, and you must add it before np.isnan, meaning that here we are skipping or removing the nan values in the img, just like this. Now the data gets clean here, like this, and finally function returns original test on clean data, the data that nan values skipped. So now the original test.clean, as the mk original test has different outputs, we want to select the slope output that refers to Senna slope function. So let's run a function here, and now in the next step we want to apply this function on multidimensional data or DS variable. So now another variable must be created. Slope map equals to from XR, X array, apply U function. There it is. Now we can apply actually slope function on multidimensional data. Let's call the sen function first, the function we already created. The next argument is the variable. The variable here is the monthly temperature dataset, and the band in the monthly data is mean 2-meter air temperature. The next argument input core dimensions. It's time because we want to monitor the changes over the time, and it is very important. The next is output D types. The output D type must be float, and the next parameter is, for example, dusk allows you to parallel actually processing in the Colab environment and allows and provided higher speed of processing here. So, and the next one here, you can have a preview about the process, and remember that vectorize also must be true. Vectorize equals to true. These are necessary arguments when you want to apply, for example, the slope for a multidimensional data. Let's run a function. Now we are waiting to see the results. Takes couple of seconds. It depends on volume of data. Higher volume, higher time actually, or takes longer time for the processing. If you faced with any issue or problem, you can compare your code with mine, and feel free to reach me out on my channel. After 33 seconds, the process is done, and now slope map is created. Just print it, and you can see a multi-dimensional output for the same region of interest and array values. How to plot it? It's very simple. Slope map dot plot. Still we have longitude and latitude. As long as lon and lat is available, you can have a visual, you can also visualize the spatial variation over the time. X sets to lon, y sets to lat, and robust equals to true. Okay, no need to call because here we will have a single map that shows how temperature in each pixel changed during the time. Okay, let's run a plot, and now you can see a new plot that shows where temperature increases and where temperature decreases. Positive values shows increasing temperature, the negative values shows the decreasing temperature. For example, in this area, we have a cold spot that shows the temperature over the time a little bit decreased through the time, and the unit is based on the Kelvin. How much temperature increased based on Kelvin and how much temperature decreased based on Kelvin. The red region, for example this area, Western Iran, temperature increased about 0.006 Kelvin during the time. So you can see such kind of analysis in the Earth engine and also Colab environment thanks to XEE library is really accessible and easy to use, and you can actually use a lot of machine learning methods to get more estimations and to get more information about the satellite data you are working. I hope you liked this tutorial as much as I did, and feel free to use this tutorial for your own research and projects. Just asking you to share this tutorial with other people who are interested in remote sensing and geospatial data analysis. Thank you for your attention.